So in boosting, the idea is we want to convert a weak learner into a strong learner. So a weak learner, let's try to define these terms vaguely. It's not too important, the specific things, but at least it's the intuition. So okay, for this section, when we're talking about boosting, we're just going to focus on, for simplicity, binary classification. That is, we're doing a classification task and we want to label things as either 0 or 1. So if you do any classification task, you can actually get a pretty high accuracy in terms of just in the grand range of things. Like your accuracy of any classifier can be between 0 and 100%. And I claim you don't even have to look at your data and you can already get halfway there for any specific point. That is, imagine a classifier which just takes your data, given any point x, it'll just predict randomly whether 0 or 1. Well, it's essentially got a 50% chance of getting it right, and therefore a trivial classifier is one which just guesses randomly and gets 50%. So now what a weak learner is something that does maybe a little bit better than that. Not quite just random guessing, but say like a little bit better, say like 55% accurate. The 55 isn't super important here. The most important thing is like that this is like better than random guessing. Well, so the idea is, given some sort of weak learner, a learning algorithm which can do a little bit better than guessing, can we convert that into a strong learner? And this isn't something like, I'm not going to give a real formal definition of what it means for a strong learner, but this is maybe what you think of as a learning algorithm. Like, I don't know, I'm just going to put this in quotes to see how, like 90% plus accurate. There's no real guarantees that we get in terms of like the test error guarantee in general. Into general settings, and that's not really the focus, but the idea is like we're taking something which is just a bit better than guessing, but somehow we want to convert this into something which is very much more accurate. And let me try to give you a caricature of how this process will go. This might not make the most sense right now, but we'll revisit a picture like this. So let me start by drawing some data set which looks something like this. Let's say our data set looks like that, and our minuses, our pluses and minuses look like this. Now, the idea behind what we're going to do in this boosting type procedure is we're going to generate a sequence of learning algorithms which each learn some of the space that we're trying to learn. And then based on what previous ones didn't learn, then we're going to boost the importance of things that we haven't looked at yet. So for example, let me try to be a little bit precise. Let's suppose we run a learning algorithm on this and we find some sort of classification thing that looks something like, I don't know, this. This is not bad. Okay, this is much better than a weak learner, but don't worry too much about that. The idea is that first we've basically learned what the classifier looks like correctly on this space, and as well as a lot of this other space. But you'll notice that there's some area that we haven't really done too well. So for example, this space right here, let's say a different color. This space right here, we have not learned well yet. So once we have this first classifier, what we can say is, okay, this area in here is not that important because we've already learned it with one classifier. This area, the blue area over here, is not super important because it seems like this classifier already gets it right. But which area is the classifier wrong in? The classifier is wrong in something like that looks like this area right here. So therefore, we're going to kind of downweight everything that we already know well, but we're going to upweight everything that we have here. And after we do that type of weighting, then our new classifier will know, okay, we have to really learn these points well, and then we'll learn another classifier that looks maybe something like this. And then from there, we have one classifier which learned the first space and one which learned the second space over here, and putting them together in the right way will do something good. So that's just a caricature, but the idea behind how boosting is going to work is we learn some points, then we find out which ones we didn't learn, and then focus our algorithm on those ones. So that's what we're going to build up to. I'm going to warn you, it's going to be a little bit of a trek to get to that, in perhaps seemingly unrelated topics, but we'll get there eventually. And along the way, we're going to go through some of the most fundamental and beautiful topics within machine learning, statistics, as well as computer science, in the sense that the key setting we're going to go through is something known as online learning with experts. And we're going to introduce what's known as the multiplicative weight update rule. Multiplicative weights comes up everywhere in computer science. So it's really something that you'll probably, in statistical settings especially, it's something that you can see again and again and again. So yeah, if this is your first introduction to it, consider yourself lucky that you get to learn this for the first time, because I think it's really beautiful. So we're going to be focusing on the setting with online learning with experts. And let me try to motivate this first with a sort of maybe a bit whimsical of a setting, but then we'll describe the setting more abstractly. So the whimsical setting you can imagine is, suppose you're going to a horse track. This is a common example used to introduce this, like horse racing, where you imagine that there's going to be so let me just sort of note down some of these things. Example. So the example is going to be horse racing. And you know that there's going to be T races at of some horses someday. And there's going to be N horses that you want to bet on. And the idea is that for each of these races, you want to pick some way to bet on these horses in order to, say, maximize your winnings. So you don't really know too much about the horses before the day begins. So in the first race, maybe you bet some way, but then based on how they perform, then you can change your bets for the second round. Because maybe you see that one horse does well, and so maybe you'll invest a little bit more in that horse and want to bet heavier on it. And then you do it again and again and again. And the idea is, how well can you do in terms of betting on these horses, in terms of how much can you make, essentially, how well can you bet on these horses, and how would it compare if somebody told you that this is going to be the best horse today, just put all your money on it. How does your strategy compare there? So again, this is a little bit whimsical, but let me try to define the setting a bit more precisely. So let's draw a line so that we see that we're in like a kind of this setting, but this example is just for show. So there's going to be T rounds, and at each round, an algorithm has to pick weights over different items. So there's going to be T rounds. At round, say, lowercase t, the algorithm picks weights P1, T, such that summation of EI T equals 1. So the idea is, first thing that's going to happen is there's going to be n different things, broadly speaking, and the algorithm has to pick some weights based on, it has to pick how it wants to weight these different things, and you can think of them as the horses in the previous example. So then the algorithm experiences, or it receives, loss of the following form at time t. the loss is going to be of the form p sub t inner product with L. So yeah, this is the loss experienced by the algorithm. So what is this? This is just the inner product of the weights that the algorithm picks for these n different items. And this is going to be an adversarially picked loss. That is between 0 and 1, the n. So to draw it into our metaphor that we had, in the first round, at each round, the algorithm will pick weights on the elements. So that kind of can be seen before as how much you want to bet on each horse. And then at that time step, the algorithm will experience loss sort of proportional to these weight. There's going to be some unknown loss vector, and then the loss you experience is going to be the inner product of that loss vector with the with the amount you sort of bet on each horse. So this is kind of backwards in the sense that the way that you might have intuitively thought of this is you want to bet more on the best horse, but maybe you can think of this as like how much you lose each time, how much you lose with each bet. Okay, and so that is essentially all that happens in the sense that the algorithm picks some weights and then experience losses, and then it repeats again and again. And then the goal is naturally to minimize summation of the inner product of p sub t and L sub t from t equals 1 to capital T. That means the algorithm is really trying to figure out how to pick these p's, these weights on the different horses or on the different strategies that it can pick, how to pick these p's such that it minimizes the overall sum of these inner products. Now, this might seem like really impossible to do well, because remember, these are picked adversarially in the sense that the algorithm can pick these p sub t's, and then immediately after that, the adversary can take a look at this p sub t and say, okay, you put a lot in one coordinate, well, we're going to make the loss function so that it's very, very large there. So somehow, it seems like this is an impossible task, just based on the fact that this loss function, the loss at each time, which is a vector between 0 and 1 to the n, well, this can be picked really to mess up your day. But it turns out that miraculously you can still do well and still get a fairly small value. The question is, how do you just define the benchmark? Like, how well can you do? And the kind of benchmark that we compare with is, like I said here, this was kind of picking the best horse in hindsight. Well, the best single choice in hindsight is going to be the following. So the benchmark, kind of what we attempt to compete with, we can't really do better than this, is we want to compete with the min over I equals 1 through n of summation L I sub t from I equals t equals 1 to t. So yeah, to try to convince yourself that this is the same thing as if you just picked p sub t is equal to 1 in coordinate argmin for I of right. Try to convince yourself that if you just picked one strategy and stuck with it for the whole time, that corresponds to when you set this p vector just to be a 1 in the specific coordinate. Then this would correspond to just plugging in a 1 here for the appropriate thing, and it would pick out L sub I, and just summing that up. So right, hope that makes sense. This is what we're trying to minimize, what our algorithm receives, and we're trying to compete with the best in hindsight. And so this is the setup for this problem in like online learning, which may seem a little bit different from the type of learning we've done so far in this class, but that's fine. It's just a different setting, and we're going to relate it back in a little bit. And the algorithm that turns out to be good here is an algorithm which is known as hedge. This is a classic algorithm, and it's parameterized by something called beta. So I'll note that, not known as beta, it's just a parameter, the parameter that lies within 0 and 1. So the algorithm will be as follows. So the idea is going to be as follows. We're going to essentially maintain some weights over the different options, and those kind of reflect our idea of how good those options are. And if we just keep updating this and doing this step by step, then it turns out that will give us something which is competitive with this benchmark right here. So, okay, let's see what we do. First of all, we start by initializing our parameter vector to be just uniform in all things, meaning, before we start, imagine before you go to the horse races for the first time, you don't know anything about the horses, and so you just pick that they're all equally good in some sense. But once you do that, then we sort of start our iterations for t equals 1 through capital T. What we're going to do is, first of all, we're going to remember these are just some weights, but we want these p 1 through n, which are a distribution, that is a sum to 1. So we're going to normalize this. So for now, it actually is a distribution. It starts off like that, but it's not going to stay like that for now. So just to be safe, we're just going to set p sub t is equal to so essentially all this is saying is we normalize, convert these weights into a distribution because you're dividing by the sum. Okay, so those are our weights. And now, based on this, we know what our loss is in the sense that the algorithm has to pick these PTs. Well, we just picked it. So we receive loss, which is, again, just think about it for a sec. We just, as we defined it, it's going to be P sup T inner product with L sup T. This is the loss that the algorithm received at this time. And now the key thing is, what do we do as a result of these losses we get? Like, how do we choose what these weights are? These weights, so far we haven't touched them. Well, the idea is that we are going to essentially change the weights of these W's based on how much loss we observed. So to say this another way, imagine you were betting on different horses. Well, if a horse does very well, then you would want to bet more on them. And if it didn't do well, then you'd want to maybe bet less on them. So this is natural. The question is just how specifically to update things. And we're just going to do it as follows. We're going to take our own old weights, and then we are going to multiply it by this constant beta, so there's a constant here, raised to the power of L sub I to the sub t. So this is known as the multiplicative weight update. And the reason why is because, I mean, it's kind of intuitive. We have this as our old parameter, and we just multiply it by something in order to update it. So you can see, let's try to interpret what this update is. So remember that beta is just some number between 0 and 1. So it's going to shrink these weights somehow, depending on how small or large the exponent is, it says how much we'll shrink it. So, okay, let's just suppose it's something simple like, I don't know, pick say 0.5 if you want to visualize how these updates will work. So, okay, let's suppose the loss is 0. That means you don't incur any loss. Well, that means that's a very good horse if you don't lose anything from betting on it. Well, you would take this 0.5 to the 0, which would give you a 1, and essentially you would just keep the weight the same. So that is, if your loss is very, very small for a given, at some time step for some specific item, for some specific horse, you can say, then you keep the weights exactly as it was before. However, on the other hand, at the other extreme, suppose the loss was very large, say the loss is equal to 1, then you just multiply this the old weight by this factor, which recall is less than 1. Say it can be 0.5. That means if something incurs a large loss, then you would shrink its weight a lot. So that's essentially how this works. The main intuition is if a specific horse or a specific item is good, then you keep its weight roughly the same as what it is. And if it doesn't perform well, then you shrink its weight a lot. And properly doing it just is in this multiplicative way. So that's the whole algorithm. And you just repeat this every time you normalize your weights, then you receive some loss, and then you perform the multiplicative weight update rule. That's how it's sometimes called. Very, very simple algorithm. And yeah, the question is, how well does this algorithm really do? Does it does it achieve what we wanted? Well, obviously, otherwise I wouldn't have set it up like this. But yeah, the idea is that indeed, it'll get us a fairly low loss in comparison to this benchmark of the best in hindsight. So let me write out what the guarantee is. So the guarantee that we get from this algorithm is the following. So remember, what we're trying to measure is here, product of P from T equals 1 to capital T. So this is our kind of, so to speak, our total loss, in the sense that if you look at what the algorithm has to, what the cost it incurs over the entire course of the algorithm, it's just summing the loss at an individual round over all T rounds. And there's a claim, which I'm not going to prove for you, but you can upper bound this total amount of loss by the following quantity. You can look this up if you care. It's in, I think, some of the readings I reference. So yeah, this kind of funny looking term here. Let's try to parse some of these things here. So let's recall that, well, what are these various things? So we have to pay some cost, which is logarithmic in the total number of items or horses that we're considering. You can see that there's this beta here, which kind of shows up as a balance between the two terms, in the sense that if we, picking beta larger or smaller will kind of balance between how much we pay for this log n versus this term over here. And you can see here that this term over here essentially is that same benchmark that we set earlier, the best option in hindsight. So this is an expression that it's possible to prove, and we're not going to do that today. You can read the notes if you care about it. So this is a bound you can prove on how big the total loss is, which is in comparison to the, well, let me say, best option in hindsight. And make sure you understand why I call this the best option in hindsight, because it's really just saying that you pick one at the beginning and you put a 1 there and a 0 everywhere else in our vector here, and you stick with it the whole time. Of course, you can't do this at the beginning because you don't know what it's going to look like in future rounds that haven't happened yet, but it's the best option in hindsight. Cool. So that's the type of bound you can get. Let me note that there's sort of a right choice of beta. So if you choose beta here to balance these terms appropriately, then you can get something like the following. So let me say set beta, and then we'll get the following. So we'll write it like this. We're going to normalize by capital T, just for some sake of comparison. So again, this is going to be, this here is our total loss, but by normalizing, this is our average loss, where this is the average over the different rounds. So that's that, and like I said, with the appropriate setting of beta, I'll just claim, I'm not going to do this out, but I'm going to claim that you can write this as follows. So this is the bound that you end up getting, which is actually quite appealing for reasons we'll talk about. So this right here, well, we notice that this is the the best loss in hindsight, this term right here. So this here is the average best loss in hindsight. And again, this is kind of the case where you pick something at the beginning and you just stick with it and you make the best possible choice. And this term here is known as the regret. And why is it the regret? I mean, it's basically the regret you had, your algorithm will accumulate over the course of the algorithm because it's the amount of extra loss you have as opposed to just picking the best thing in hindsight. So yeah, it's called the regret. And the important thing to note is that this goes to zero, approaches zero as t approaches infinity. That's really cool because of the fact that, yeah, essentially, what this statement here says is, it might not be obvious, but it says that you can predict the future in the sense that if t is long enough, the average loss in each round of this algorithm is going to be comparable to the average loss of just picking the best thing after you've seen it all, which of course you can't do if these are coming to you one by one. So yeah, it somehow allows you to be very, very competitive, even though that would require you might think that this is impossible and would require you to predict the future. But this type of thing is called no regret learning because this regret goes to zero as t approaches infinity. So yeah, this is a very important algorithm, and I think it's very beautiful, the fact that it lets you do something which is very counterintuitive, and I wouldn't think a priori that this is even doable, but it does it via this very, very simple algorithm right here, which is like 3 lines. So yeah, if you're interested, you can definitely read a lot more. This is ubiquitous in computer science, and knowing it well, I think will help you out in your future career if you're interested in really understanding cutting-edge algorithms in machine learning and statistics. But okay, we're not going to go into the details of that. We're just going to try to talk about how this can be used for, say, more familiar machine learning problems, things which, like, we just want to do classification, and how can we take this back to what we were talking about before, where we're trying to maybe downweight some points and upweight certain other points and like go from there. So okay, let's go back to the setting that we care about. Let's recall what it is. Given an algorithm, which we'll call, say, weak learn, that gets, say, like greater than 50% accuracy. Let's say greater than 51% accuracy. On a training set. So the question is, suppose we have something that gets 51% accuracy, or something which is close to just a little bit better than random guessing. The question is, can we boost it to high accuracy? And I claim this can be done using this magical algorithm that I told you about here, which might seem totally unrelated, but it turns out that it can be done in a pretty natural and, I'm not going to say fully intuitive way, but kind of intuitive way once you think about it a little bit. So let me tell you the most immediate way you might think of doing this, and it's the wrong way. I'll tell you, this is kind of like why I said it's not the most immediate thing, because the first way you'll think about this is just flat out wrong. And the intuitive way is the following idea. You know, we're thinking that maybe you have an algorithm which can just do a little bit better than random, but you don't know which one it is. So maybe you might think that you run this algorithm a bunch of times and you set them as the different experts, like the different horses. You let the algorithm, like results of this algorithm, be the different horses, and somehow you run it many times, and maybe you figure out which ones it does well on and which ones it does poorly on. Yeah, so that's one way you might think of it, but this is not the right way. So the algorithms are, I'll put this in quotes, horses, because we used this metaphor before. This is not, they're more commonly just in, so that you don't go telling people about horses all the time. These are kind of like the more standard way of referring to them as experts. So the wrong way would just be to do the algorithms as the experts, and, you know, maybe the goal is to put large weight on good algorithms. So it's not exactly clear how you might actually execute this, but it seems intuitive enough, right? You're trying to pick out the good ones, so you somehow get large weights on the good ones. But this turns out to not be the right way, and instead what we have to do is something slightly different. And we're going to use this intuition that I kind of mentioned way back in this drawing over here. The idea is that we're going to try to upweight points which are not yet well learned. So in other words, our data points are going to be the experts, and a large weight on a point means we haven't learned it yet, so our algorithms need to focus well on that point and do well on it. So let's try to sort of summarize this from a high level, and then we'll maybe get into a few more details. So the right way is the following. The data points are our experts. And the intuition, like I said, is a large weight means that still must learn this point. Okay, so that's the main idea. Let's essentially just write out what the AdaBoost algorithm is, which stands for adaptive boosting. So it's essentially going to be the exact same thing as this algorithm hedge that we had here. You know, this very simple algorithm, which is just a few lines. The main difference is, first of all, the setting in particular. Okay, to instantiate this algorithm, basically what you have to do is come up with how you're going to define these losses. Everything else is really just like set in the sense that the rest of the algorithm runs itself, but you can choose how to control the algorithm by defining how these losses come. And yeah, so it's just going to be an instantiation of it. The other difference is that we're going to have a dynamically changing beta. And this is because, is there a good way of saying it? Like, the name AdaBoost means adaptive boosting, meaning that we're going to change how much we learn at any given time, depending on how how much we need to update things. So this is a bit vague. So let me try writing down the algorithm, and then you might see why this is important. So the same thing, we just start the same way. We start with setting weights to be uniform because we don't know a priori. A priori, we want to learn all the data points equally. None of them are learned yet. So yeah, we're going to, in some sense, be looking at weightings of our data set. And what I mean by that is if we just have this uniform weighting of the data set, then it just kind of means that one way to picture it is that 1 out of the n points in our data set are going to be that specific point. So this is a vector of length n, so the first point is going to have weight 1 over n, meaning there's only one copy of it, and so on for every other thing. Now this is going to change over time. For example, something could be, say, 2 over n. And if it's 2 over n, that means kind of that you're going to have 2 copies of it in your data set. There's other ways to do this, like without making copies of data points, but that's at least the intuitive idea, that you can think of it as either making copies of data points or removing data points entirely, stuff like that. But initially, we're just going to start by setting it off that everything is going to have weight 1 over n. So we're going to have this main loop again for t equals 1 to t. And we're going to set our p exactly as we did before. So we're just going to normalize this distribution, or normalize these weights rather, to make it into a distribution. This is sum over all I in the vector. Sorry, this is not well written, but there's an n here. So that's the first thing you do. You convert these weights into a distribution. And now the sort of key thing before, what we did was right, we just sort of took the inner product with these losses. But the thing is, how do we penalize our algorithm? How do we want our algorithm to learn? Well, this is where we essentially use our weak learn algorithm. Remember, we assume that we had some weak learn algorithm that gets, say, 51% accuracy on a training set. So we have something like this. What we do is run weak learn on training set with weights w sub t, or not w sub t, like with weights p sub t. So yeah, the idea is that you essentially reweight your training data set according to whatever weights. Originally, it's just going to start uniform, so you train as normal. But if you find out that at some point that there's some points which are going to be more important, then you're going to upweight those points, maybe by making duplicates, and other weight points you're going to downweight. That's what this means to run it on the training set with these weights. And then this will give you some algorithm or some classifier which hypothetically does well on this reweighted training set. And we're going to say it gives you predictions between 0 and 1. It's a binary classification problem, but it's going to give you some sort of confidence or something between based on how likely it is. Kind of similar to SVMs, which kind of tell you, or let's say more like logistic regression, I guess, because it gives you sort of confidences on how likely it is to be a 0 or 1. So yeah, the idea is you run this weak learn algorithm to get some classifier, which is just a little bit better than guessing on the training set with these weights. And then what you do next is you calculate the error on your training set as weighted by this. So the error is going to be defined as follows. It's going to be this epsilon sub t, which is going to be just basically add up all the error over points in your training data set. Weighted, of course, by these weights. Right. So this is kind of the intuitive thing that you would, yeah, this is kind of like, let's say that this is, let's unpack what this is. This is the error on point I in the training set. When you throw in this becomes the weighted error. So if there's certain points that are more important, then you kind of have to weight their error more than others. And then when you sum it over the entire training data set, then this kind of becomes the average weighted error. Good. So yeah, you can see that this is the error. And the idea is that our weak learn algorithm, remember what our guarantees for this weak learn algorithm are. It says that it can get, say, 51% accuracy on a training set. So this error, if you think about it, essentially the weak learn guarantees that this should be less, let's just say like epsilon sub t is less than or equal to, say, 0.5. Because again, that's the guarantee that weak learn should have, something like that. It won't always obey this. Sometimes maybe you get unlucky and it does worse, but in general, it should be something less than this quantity here. So that's the error that we calculated. This will be useful in terms of defining the losses that we're going to plug into our instantiation of this multiplicative weights update. Remember, the way the algorithm works here is that you have to take, you receive some loss, which is the inner product of the, yeah, we have to kind of define what these losses are because that'll tell us how we make these updates. So, okay, the step we do before then is we define the, what's kind of known as the learning rate. So we define b sub t to be equal to epsilon sub t over 1 minus epsilon sub t. Don't worry too much about why this is the right choice, but let's try to interpret this a bit. Like, what does this say? This says, remember that b is going to be, let me write the next line and actually we'll return to this and we'll see why. And we're only going to do this next line if, say, epsilon sub t is, say, less than or equal to 1/2, because otherwise it doesn't necessarily make sense. But we're going to do the following. So yeah, this is all in the exponent here. Okay, let's look at these lines and see if we can interpret what this means. So let's look at some of the extreme cases. Suppose that, suppose that we have, say, 0 error on our training set, so that is epsilon t equals 0. Everything is just got spot on. Then beta sub t will be 0 as well, just because it's going to be 0 over 1. And what would happen at that point is we would then multiply things by 0 to whatever power. And so these weights would immediately drop down to 0 instantly. So what does that mean? So like if epsilon t small, this implies that beta sub t is going to be small. And that implies that reduce, let me write this a bit lower. And this implies that reduce weights a lot. So that means the way you can kind of interpret this is, remember, these weights are telling you how much learning still needs to be done. The bigger they are, then the more a point still needs to be learned. So if we get that epsilon t is very, very small, that says that, okay, we're done learning and we've got we can get good accuracy on it. So we're going to shrink these weights down to pretty much 0 or something very small. Whereas on the other hand, if we have epsilon sub t is I mean, I'm not going to write it out because it's basically the same thing. If epsilon sub t is large, then beta sub t will be also large. The bigger epsilon sub t is, then the bigger this will be. And that implies that we have a higher beta here, meaning that we're going to try to keep the weights, these wi's, larger, because that means that we still have a lot of learning to do. Because if there's a lot of errors, then we still have a lot of learning to do, so we don't want to shrink our weights too much. So that's the kind of interpretation of this parameter. It's a learning rate of sorts, where the smaller it is, the sort of faster that this process will end, whereas the larger it is, then the slower progress will make. It might sound a bit backwards, but yeah, that's kind of how it works. Okay, and the final thing I'll comment in this algorithm in terms of these updates is the fact that these exponents here, which might seem a little bit backwards, but let me try to give you some intuition. Let's suppose that like this is 1 minus the error you get here. So let's try to interpret what happens again at the extremes to a weight of a specific point when you have the classifier at this time step t making prediction on it. So let's suppose that it is a good prediction, meaning that like this h sup t on xi minus yi, suppose this is small. Then you have a relatively large exponent. You take this beta to something which is larger, and therefore that's sort of shrinking it the most. Remember, this is a number that's between 0 and 1. So having a large exponent means that it'll be as big as possible. Having an exponent which is larger will make it so that this is going to be as small a number as possible, and we make the biggest possible decrease in these weights. So just to sort of summarize that, an accurate prediction means that we shrink the weight on that point by a lot. On the other hand, suppose we're totally off on it and we don't have a good prediction, then this exponent will be closer to 0. And therefore, in that case, we're going to keep, because this is the number between 0 and 1, we'll raise it to the power of a small number, and this will stay relatively large as a multiplier. And therefore, we keep the weight at the next step fairly large. Yeah, so that is the main idea behind this add a boost in terms of what we're going to be doing in each time step. We still haven't said how to get a final classifier, but it's kind of going to be the following. We're going to define a set of weights over our data set. We're going to run a learning algorithm that uses those weights with those points. And from there, we get a classifier which is good on the training data set with those weights. And the intuition is that these weights are going to try to be high if they're points which we haven't learned yet, but we're going to drop them a lot if they're points which we already do well on. And so in this way, we're going to keep getting a sequence of classifiers, each of which will learn the points we didn't really know well before, until finally, until we do this for enough rounds. So now let's suppose we've reached the end of this. What have we done? We've essentially gotten a bunch of classifiers at different times, h1 through h capital T. And we somehow want to be able to do some predictions with it. Well, I claim, I'm not going to prove this for you, but I claim a good classifier is the following. And you can check out some of the linked readings if you want to see why it's a good classifier. But in the end, we're going to somehow combine ththese h sup t's into one thing. And it's going to predict as follows. I'm going to write something rather arcane. And then I'll maybe interpret it a little bit for you, but otherwise I'll refer you to the readings. So, okay, the idea is that our classifier is basically going to take our classifiers that we learned at each step. These are our weak learners, remember? What it's going to do is it's going to re-weight these, and then it's going to basically sum them all up. It's going to do a weighted average of these different predictors, and if it's sufficiently large, this is weighted prediction, then we're going to say it's a 1, otherwise we're going to say it's a 0. Now, how do we choose, and how do we say, how are these weights chosen? Well, it's kind of intuitively chosen in the sense that it's just using the same property we said before. So let's imagine for a specific time that epsilon sub t is very small. That means, say, like epsilon sub t is going to be 0 or something. If we have a very small epsilon sub t, that implies a very that means that this classifier is really good, right? Because it means that it did well and it got a very low error. Well, if it got a low error, that means we said beta sub t very small as well. And then log 1 over beta sub t is going to be a large number. So it means that if we got a small error at that time, then we're going to weight that corresponding classifier at that time higher in our prediction. And vice versa. If it had a large error, then we would make beta t sub t be bigger, and this would result in a lower weight on that as well. So you can see that it's a bit arcane and mysterious here, but the idea is that we get a bunch of classifiers out of it, each of which we have some sort of idea of how good it is, and then we just weight it by depending on how good each different classifier is and make some prediction based on that. And yeah, that's the algorithm. Let's try to, here's a picture of what it kind of looks like in action. Yeah, this might help visualize what's kind of going on in all these things. But let's suppose we have some sort of original data set here, pluses and minuses. This is pictures from Yao Liang's, Professor Yao Liang Yu's course. I just took it from his slides. But you can see here that this is a sort of caricature of what goes on. So you imagine you have some positive and some negative points. And what you do first is you train some sort of classifier, which is a bit better than random guessing. So suppose it predicts here this bottom half is red and this top half is blue. And it's good on many of them, but you'll notice that it makes some mistakes. Say these two blue ones here are incorrectly classified, and this one here is incorrectly classified, this plus. So what we do is, what AdaBoost will do is it will essentially weight these things higher and weight everything else lower. So you can see here's our new data set where we've made these minuses a little bit bigger, these two that were here, and this plus here a little bit bigger, and everything else is shrunk a bit. So now, given these re-weighted points, now we're going to learn a classifier on this new sort of weighted distribution, weighted set of points, and we get this. You can see it gets right on many of these, but then these ones are incorrect. So then it increases the weight on the ones which are incorrect, shrinks everything else, and runs the algorithm again. And after a certain number of different things, a number of different iterations of this, then eventually you just output some combination of these different classifiers. And yeah, you can see that it's sort of like an appropriate reweighting of these different classifiers. And that can represent shapes that weren't there in the original thing. For example, the type of classifiers we were using, just draw vertical or horizontal lines, and you can see that you get this more complex decision boundary here. Cool. So that's the image of what you can picture that AdaBoost is doing. So let's see how, we're almost done now. Let's just sort of wrap it up and say what sort of training error we get. So like what type of guarantees do we have? We showed this complicated theorem we had in terms of the accuracy guarantee or the average loss in this online learning setting. But let's see what that, it kind of implies something along these lines of the training error. We're not going to get into why this is, but something like the following holds. So if you want to know how many, yeah, let me just write this. So this computes the fraction of points where the classifier we get, the classifier h that we end up with does not equal, which does incorrect predictions. And so there's just an indicator, so it averages. This tells what fraction of the data points in the training set you get wrong. Well, this can be upper bounded by the following. By this quantity here. So this is, remember that t is the number of rounds that we ran ADA boost for. And this is the error that we had at time t. So this is going to be something like less than 1/2, hopefully. So just to give you a concrete example, suppose you say that epsilon sub t is equal or less than or equal to, say, 1/2 minus gamma. So that means like it's bounded away from 1/2. Well, then this term here, this can be upper bounded by something like the following: x buff minus 2 times t times gamma squared. What does this mean? Well, this means that we can take t to be relatively small, like something which is logarithmic only, and this will get to be a very small training error very, very quickly. Yeah, so this dies off very quickly as you have something which is just a little bit better than random guessing. So what does this mean? What does this tell us? This means that if we want to do well on the training data set, we can do well with only a few iterations without sort of too many. Now, the thing is that this is not what we wanted. This is what we want really is we want good test error. So this is kind of like, you might think just on a glance that this is not what we want, and in fact it can even be bad, because it sounds like if you run this for a while, it'll overfit to our training data set, because if you set t large enough, then you'll drive this down to 0, and then maybe you'll overfit. However, nonetheless, it seems like this still gives pretty good test error in general. You can do better, like maybe if it'll generalize better if you have very simple classifiers. And what do I mean by simple base classifiers? I mean, remember, if you recall from the end of last lecture, I mentioned decision stumps. That is just a decision tree of height 1 or 2, depending on how you count, where you just split exactly once, and then you go with that. It turns out these are not really that much better than guessing, but if you do boosting using them, then it turns out that these can generalize surprisingly well, maybe better than you might expect. So yeah, generally when you're doing boosting, you want a very, very simple base classifier. Otherwise, you might run into overfitting. Good. Just to show you how it might compare with boosting, or how boosting compares with, say, bagging, random forests. You can see this is another data set here, which I'm not going to get into. This is a figure from the Introduction to Statistical Learning book. And you can see that as you increase the number of trees past a certain point, then it starts to become roughly flat and doesn't really change much. But you can see that boosting with either, say, the depth refers to, say, the depth of the decision tree, say depth 1 or just depth 2. Either way, using those as the base classifiers, that does much better than random forests using the sort of rule that we described, where you pick square root of the dimension number of different features, and you split on the best one there. So you can see that boosting can be better than bagging in certain cases. You can also find the opposite, I'm sure, in certain settings as well. But yeah, this is just to show you that this kind of works in some cases. Good. So just to finally recap, we're finally done the lecture, and today we talked about like 2 different approaches, which are boosting and bagging. And the way I would say that is that the way I would describe them broadly is they're generic and flexible methods, meaning that you can basically convert any type of learning algorithm to a better one, where I use quotes for that because it might not always be better, maybe overfit or something. But it's a generic and flexible approach to converting any classifier or learning algorithm into a better one, both of these. This, of course, comes at some cost. It's not just things for free. This can be, for example, less interpretable. what do I mean by this? Like, recall that when we were talking about decision trees, for example, this is a canonical case where these methods are used. With decision trees, we like them because it really tells you how you make a decision for a points classification. You just follow a set of rules, and a human could understand what's really going on. Whereas when you're doing this boosting, then you saw this expression here. It was kind of a little bit hairy, and it's not clear how to interpret what it means to classify something as a 1 or a 0. So it seems harder to understand how it makes decisions. And as a final note, I'll comment just about the computation, a computational aspect. So bagging is parallelizable in the sense that, remember what you do. You just do this bootstrap sampling and then run it on all of those data sets at the same time. Well, if you have enough parallel processors, you can do these all simultaneously. Whereas for boosting, on the other hand, this is a very sequential procedure. Meaning that, recall that every time you get a new distribution over your training data, so you need to run these in sequence in order to discover the new distributions each time, discover the new weights over the data set. So yeah, that's kind of one of the key differences between boosting and bagging. But yeah, that's it for today. Boosting and bagging are both very powerful methods to make a weak learner stronger.